Lesson 13.1, the last lesson. Congratulations. Comparing three or more means one-way analysis of variance. The objectives for this lesson is to verify the requirements to perform a one-way ANOVA and test a hypothesis regarding three or more means using one-way ANOVA. If you pull up your overview sheet, we are on the last addition to the overview sheet. So this is what we will be learning today. What is analysis of variance used to test? It tests the equality of three or more population means. The null hypothesis is that mu1 equals mu2 and mu3, and so on, for however many mu's you have. The alternative is that at least one population mean is different than the others. Here is an example of what this would look like. So A would be the null hypothesis, if we did not reject that. And then B, this is just one example of what the alternative hypothesis might be. There are other ways that this could look. For example, mu1 could equal mu3. So these two curves would be on top of each other, and mu2 would just be different. So remember, just one of the population means have to be different. Why do we use ANOVA to test the equality of three or more means rather than comparing them two at a time using the techniques used in section 11.3? So we use ANOVA because testing the means two at a time increases the probability of making a type 1 error. There are four conditions that must be satisfied to perform a one-way ANOVA test. 1. There must be k simple random samples, one from each of k populations or a completely randomized experiment with k treatments. 2. The k samples must be independent of each other. That is, the subjects in one group cannot be related to in any way to subject in a second group. 3. The populations must be normally distributed. We can verify normality by constructing a normal probability plot for each sample. Or B, the option is robust, resistant to errors. Small departures from the normality requirement do not significantly affect the results. And 4, the populations must have the same variance. That is, each treatment group has population variance sigma squared. So what that means is that the largest sample standard deviation is no more than twice the smallest sample standard deviation. So to sum this up, 1, they must be random. 2, independent. 3, normal. And then 4, the largest standard sample deviation is no more than twice the smallest sample standard deviation. Another way to verify the normality requirement, option 3 here, or criteria 3 I should say, is a one-way ANOVA test is through a residual plot. So part 3b from above. The residual of each value is the difference between the value and its sample mean. Once the residual has been calculated for each value in each sample, create a normal probability plot for the residuals. If the residuals are found to be normally distributed, their normality requirement is satisfied. To verify the normality requirement by analyzing residuals, we're going to use number 23 on our calculator sheet. We're going to verify the normality requirement for the data analyzed in the example below by this residual method. So let's scroll on down. let's look at this example. So we're going to apply this portion, number 23, to number 3 on this example. Prosthodontists specialize in the restoration of oral function, including the use of dental implants, veneers, dentures, and crowns. Because repair of chipped veneer is less costly and time-consuming than complete restoration, a researcher wanted to compare the shear bond strength of different kits for repairs of chipped porcelain veneer and fixed prosthodontics. He randomly divided 20 porcelain specimens into 4 treatment groups. Group 1 specimens used the Courgette system. Group 2 used the Sillistor system. Group 3 used the Sirma system. And Group 4 used the ceramic repair system. At the conclusion of the study, shear bond strength in megapascals was measured according to ISO 10477. The data below are based on the results of the study. Verify that the results to perform one-way ANOVA are satisfied. So the first one was, are they random? Specimens are randomly assigned to the repair systems. You can see that right here. Step 2 are the independent. None of the specimens is related in any way, therefore it is independent. 3, normal. Is this normal? Let's pull up our calculator sheet. 23, very last one. We're going to go to Stat, Edit. In list 1, we're going to type in the sample values. So as you can see in the first list, we have Courgette. So I'm going to put all of those in list 1, and then right after that, I'm going to type Sillistor underneath. So let me do the first 10 or so with you, and then I think you'll get the idea. All right, so this is Courgette, and then follow Sillistor, so type those in, and then Sirma, and then ceramic repair would be next. You can see here we have all 20 data points in list 1. Now in list 2, we need to type the corresponding sample means. So let's go back, and in list 3, I'm just going to type in the first 5 for Courgette. So this is in list 3. Let's go to the main. Let's go to Calc and 1 variable stats for list 3. Here the mean is 16.28, and then you're going to want the sample standard deviation for step 4. So I would copy that down as well. So 2.36, because we're looking at the sample. So I'd like you to pause the video and repeat that for the next 3 different shear bonds. So we had 16.28, and then the sample standard deviation was 2.36. Okay, you should have done all of the next ones, and you should get 17.64, 10.64, and 10.78. Sample standard deviations 2.60, 4.22, 2.28. Go back to Stat, Edit. I'm just going to clear this list. The calculator sheet said put the corresponding means. So 16.28. There are 5 data points, so I'm going to type that 5 times. Then we have the next group, Sillistor, and that mean was 17.64. So I'm going to type that 5 times. And then 10.64 5 times, and then 10.78 5 times. Okay, so let's go to our calculator sheet. So we did number 2. We typed in the corresponding sample means. Now go to list 3, type in L1 minus L2. These are the residuals. And now we can plot these. And that is in list 3. Graph, zoom, number 9. In here you can see it's pretty linear. And if I give you a correlation, if it's greater than the critical value, we can say it's normally distributed. So this is an option, or you could have done it per list. So you could have plotted it list 1, and then list 2, list 3, then list 4. List 2 looks not too close to linear, so when you do it this way, you can tell that overall it is normally distributed. So just going back up to this one. This was not covered in this course, but the correlation for that line that we just found was 9.991, and the critical value for the amount of data points we had was 0.951. Since our correlation was greater than the critical value, we can say it is normally distributed. You would be given this information on your homework, so as long as you know if it's greater than, and you can find the critical value off of a table. I believe I talked about that in chapter 10 or 11. You know then it is normally distributed. And then 4. 4 was stating that the largest sample standard deviation, which is 4.22, is no more, so less than twice the smallest, which is 2.28. Is 4.22 less than 4.56? Yes. So we can say the largest sample standard deviation is no more than twice the smallest sample standard deviation.